if you were to imagine a box full of sand, and let's say that the sand looks sort of like this. We're sort of seeing through the box. We've got some high spots and some low spots. And maybe there's like a little sand castle in the back, so there's another little hill, and then there's some valleys and whatever. It's a box full of sand, but it's not all even, right? There's high points, there's low points, whatever. If you were to stomp down on all of this sand, if you were to squish the sand castles and level it all out and hop all around this thing, jump all over the place, so that the sand was all perfectly flat. All around the box, it was perfectly flat. If you were to do that, what you would be finding by measuring the height of the sand would be the average height of the sand at the beginning. So at the beginning, when we had all these low points and high points, if you were to take every single spot and measure the height of the sand, every single height, take all the heights of the sand everywhere, so you'd have an infinite number of measurements, right? I mean, if this was an actual thing. If you were to take all those heights, add them all together, and then divide by the appropriate infinitely large number, you would find the average height. And that would be the same as, like I've said, that would be the same height as if you were to smash all this stuff down, get it all to the same level. And this really is the idea behind the mean value theorem for integrals. So let me show you how this is going to work. So we've got some function f of x, and let's give ourselves an interval from a to b. And let's say that we want to find the average height of f of x between a and b. So we're noticing that we've got all these heights. We've got a height there, we've got a height there. All of these are different heights measured by f of x. What I want to do is find out what is the average height. And by the way, the reason that this might be nice to know, let's pretend that f of x is measuring the temperature throughout the day, and it goes up and down and up and down. And I want to know, what was the average temperature on that day? Whenever you hear those statistics on the news, like today the average temperature was 23 degrees. That is calculated by the mean value theorem for integrals. All that data is tracked throughout the day, and it's averaged by the formula that we're going to look at here in a second. So you already know how to find the average of something, or the mean of something. You add the number of things up, and you divide by the number of things that you counted. So the average between 2 and 4 and 7 would be 2 plus 4 plus 7, all divided by 3, because there's 3 things that we're counting. And it's no different here. What we're going to do is we're going to add up all of the We're going to add up all of the heights from A up to B. We're going to add all these f of x values up, and we're going to divide by the appropriate number. And the way that we add them all up is we, first of all, recognize that we have an infinite number of heights between A and B. So I want to add up an infinite number of infinitely small heights. This is the principle behind the definite integral. So we're going to go like this. We're going to take the definite integral from a to b of f of x dx. And again, what this is the summation, or the addition, of all of the heights from a to b. And now I want to just divide this thing by however many things I've got. And the number of things that I've got are all of the things that live in between A and B. If I say that, let's say that 2 people are standing on a number line, one of them is at 10 and one of them is at 2, and if I ask what's between them, the answer is 8. In the same way, I should say that we get that by subtracting, right? 10 minus 2. So in the same way, we're going to get our value for the denominator here by taking b minus a. b minus a. So this is our mean value theorem, the integral from a to b divided by b minus a. You don't usually see it like that. Usually this is pulled out front, and we multiply it by 1 over b minus a. So let's write that. This is the way that you're most often going to see the mean value theorem. And there it is, 1 over b minus a times the integral from a to b of f of x dx. So really just think of this as like averaging anything else. And there's one other thing that we should say here. This is actually equal. Sometimes we're asked to find the c value that satisfies the mean value theorem. And so what we're going to say is that all of this is just equal to some f of c, where c is a number that lives in between A and B, which we can say like this. This little e means is an element in the interval from A to B. Or we can just say that C is between A and B. So what this guy is, if we go back to our picture, we're saying that somewhere in between here, like if you were to imagine stomping down between A and B, take your boot and stomp it down, it's all going to go to some height, maybe like right there. Or maybe a little bit lower. Yeah, it'd be a little bit lower. But what we're saying is that there's some value of C that already is at that height. There has to be some value of C in between A and B that is already at the height that is the average height of all of these heights in between A and B. So here's how you might see this show up. Here's your problem. Find the value of C guaranteed by the mean value theorem for the function f of x, which is 9 over x squared, on the interval from 1 to 3. We include the endpoints 1 to 3 because we have square brackets. So let's go ahead and try to figure this thing out. I'm just going to start by writing this formula. This equation can be used whenever we are solving a problem like this. So here's my average value. It's all equal to f of c. I want to find this value of c. That's my goal. So let's just start by trying to figure all this stuff out. My interval from 1 to 3, a is 1 and b is 3. So those are going to give me my my coefficient, it's going to give me my coefficient value of 1/2. My integral is going to be evaluated between 1 and 3. F of x is my function, 9 over x squared. And now we simply evaluate this. And this is all, by the way, equal to f of c. So let's try to simplify it one piece at a time. It's going to be 1/2. And then I'm just going to put the antiderivative in some brackets. Remind yourself that 9 over x squared is the same as 9 times x to the negative 2 power. So raise the power by 1 to get x to the negative 1. And then we need a negative 9 out front to get our positive 9, because negative 1 times times negative 9 is positive 9. So that's my antiderivative. I'm going to evaluate between 1 and 3. And let's see what we get. So here I'm just making my negative 9 times x to the negative 1 equivalent to negative 9 over x to the positive 1, and then I've plugged my values in, and this is going to give me 1/2 times negative 3 plus 9, which is 6, and 6 times 1/2 is 3. So all of this, the average value of my function is 3 in between 1 and 3. And what I'm looking for is the value of c that gives me 3. So my equation now simplifies all the way. I'm going to go to the next page here. It simplifies all the way down to f of c is equal to 3. Now, the question is, what is f of c? And if we remember that f of x is the function, right? 9 over x squared. I can just replace x with c and write this as 9 over c squared is equal to 3 and solve this thing. I can multiply both sides by c squared. And I've got 9 is equal to 3 times c squared. Divide by 3, and c is going to end up here equaling the square root of 3. And it's worth noting that the square root of 3 falls within the range from 1 to 3 on our interval. And so that's good. The square root of 3 happens to be 1.73, so it's within that range. So this is an application of the intermediate value theorem that you could see.